How to determine the frequency of each class. This can be done either by tally sheets or by mechanical aids. Under the technique of tally sheet, the class groups are written on a sheet of paper commonly known as a tally sheet, and for each item a stroke, usually a small vertical line, is marked against the class group in which it falls. The general practice is that after every 4 small vertical lines in a class group, the 5th line for the item falling in the same group is indicated as horizontal line through the said 4 lines, and the resulting flower for it represents 5 items. All this facilitates the counting of items in each one of the class groups. An illustrative tally sheet can be shown as under. Tabulation. When a mass of data has been assembled, it becomes necessary for the researcher to arrange the same in some kind of concise and logical order. The procedure is referred to as tabulation. Thus, tabulation is the process of summarizing raw data and displaying the same in compact form, i.e., in the form of statistical tables for further analysis. In a broader sense, tabulation is an orderly arrangement of data in column and rows. Tabulation is essential because of the following reasons. 1. It conserves space and reduces explanatory and descriptive statement to a minimum. 2. It facilitates the process of comparison. 3. It facilitates the summation of items and the detection of errors and omissions. 4. It provides a basis for various statistical computations. Tabulation can be done by hand or by mechanical or electronic devices. The choice depends on the size and type of study, cost considerations, time pressures, and the availability of tabulating machines or computers. In relatively large inquiries, we may use mechanical or computer tabulation if other factors are favorable and necessary facilities are available. Hand tabulation is usually preferred in case of small inquiries where the number of questionnaires is small and they are of relatively short length. Hand tabulation may be done using the directly tally, the list and tally, or the card sort and count methods. When there are simple codes, it is feasible to tally directly from the questionnaire. Under this method, the codes are written on a sheet of paper called tally sheet, and for each response a stroke is marked against the code in which it falls. Usually after very 4 strokes against a particular code, the 5th response is indicated by drawing a diagonal horizontal line through the strokes. These groups of 5 are easy to count and the data are sorted against each code conveniently. In the listing method, the code responses may be transcribed onto a large worksheet, allowing a line per cache questionnaire. This way a large number of questionnaires can be listed on one worksheet. Tallies are then made for each question. The card sorting method is the most flexible hand tabulation. In this method the data are recorded on special cards of convenient size and shape with a series of holes. Each hole stands for a code, and when cards are stacked, a needle passes through a particular hole representing a particular code. These cards are then separated and counted. In this way frequencies of various codes can be found out by the repetition of this technique. We can as well use the mechanical devices or the computer facility for tabulation purpose in case we want quick results. Our budget permits their use and we have a large volume of straightforward tabulation involving a number of cross breaks. Generally accepted principles of tabulation. Such principles of tabulation, particularly of constructing statistical tables, can be briefly stated as follows. 1. Every table should have a clear, concise and adequate title so as to make the table intelligible without references to the text, and this title should always be placed just above the body of the table. 2. Every table should be given a distinct number to facilitate easy reference. 3. The column headings, captions, and the row heading, stubs, of the table should be clear and brief. 4. The units of measurement under each heading or subheading must always be indicated. 5. Explanatory footnotes, if any, concerning the table should be placed directly beneath the table, along with the references symbols used in the table. 6. Sources from where the data in the table have been obtained must be indicated just below the table. 7. Usually the columns are separated from one another by lines which make the table more readable and attractive. Lines are always drawn at the top and bottom of the table and below the captions. 8. There should be thick lines to separate the data under one class from the data under another class, and the lines separating the subdivisions of the classes should be comparatively thin lines. 9. The columns may be numbered to facilitate reference. 10. Those columns whose data are to be compared should be kept side by side. Similarly, percentages and/or averages must also be kept close to the data. 11. It is generally considered better to approximate figures before tabulation, as the same would reduce unnecessary details in the table itself. 12. In order to emphasize the relative significance of certain categories, different kinds of type spacing and indentations may be used. 13. It is important that all column figures be properly aligned. Decimal points and plus or signs should be perfect alignment. 14. Abbreviations should be avoided to the extent possible, and ditto marks should not be used in the table. 15. Miscellaneous and exceptional items, if any, should be usually placed in the last row of the table. 16. Tables should be made as logical, clear, accurate, and simple as possible. If the data happen to be very large, they should not be crowded in a single table, for that would make the table unwieldy and inconvenient. 17. Total rows should normally be placed in the extreme right column, and that of columns should be placed at the bottom. 18. The arrangement of the categories in a table may be chronological, geographical, alphabetical, or according to magnitude to facilitate comparison. Above all, must suit the needs and requirements of an investigation. Graphical representation. Graphs help to understand the data easily. All statistical packages, MS Excel, and OpenOffice, or offer a wide range of graphs. In case of qualitative data or categorized data, most common graphs are bar chart and pie charts. Bar chart. A bar chart consists of a series of rectangles or bars. The height of each rectangle is determined by the frequency of that category. Suppose that the sales of a popular soft drink in the year 2010-11, in 5 geographical regions, denoted as A, B, C, D in the year 15,245, 23,762, 9,231, 14,980 and 12,387 respectively, measured in 10,000 United States dollars. A bar chart of this data is as below. Pie chart. A pie chart is used to emphasize relative proportion or shares of each category. It's a circular chart divided into sectors, illustrating relative frequencies. The relative frequency in each category or sector is proportional to the arc length of that sector, or the area of that sector, or the central angle of that sector. Suppose in the previous example, if a soft drink has its market only in the 5 geographical regions, denoted as A, B, C, D and E for the year 2010-11, the sales data in these regions are 15,245, 23,762, 9,231, 14,980 and 12,387 respectively, measured in 10,000 United States dollars. A total scale of a soft drink is 75,605 times 10,000 United States dollars. A pie chart can be plotted to have the idea of the shares of different markets. In case of quantitative data, one important chart is histogram, which is a generalization of bar chart. The data is first summarized in terms of class interval, and each bar represents a class interval. The width of the bar is proportional to the width of corresponding class interval. The area of the bar is proportional to the frequency of corresponding class interval. After class intervals in a quantitative dataset, a pie chart can also be used to read the share of each class interval. Data cleaning. This includes checking the data for consistency and treatment for missing value. Preliminary consistency checks are made in editing. Here we check the consistency in an extensive manner. Consistency checks look for the data which are unknown or not consistent or outlines. Such data may either be discarded or replaced by the mean value. However, the researcher should be careful while doing this. Extreme values or outlines are not always erroneous. Missing values are the values which are unknown or not answered by the respondent. In place of such missing values, some neutral value may be used. This neutral value may be the mean of available values. The other opinion could be to use the pattern of responses to other questions to calculate a suitable substitute to the missing values. Data adjusting. Data adjusting is not always necessary, but it may improve the quality of analysis sometimes. This consists of following methods. Weight assigning. Each respondent or case is assigned a weight to reflect its importance relative to other respondents or cases. Using this method, the collected sample can be made a stronger representative of a target population on specific characteristics. For example, the case of educated people could be assigned higher weights and of uneducated people could be assigned lower weights in some survey. Variable respecification. This involves creating new variables or modifying existing variables. For example, if the usefulness of a certain product is measured on a 10-point scale, it may be reduced on a 4-point scale: very useful, useful, neutral, not useful. Ratio of two variables may also be taken to create a new variable. Method of dummy variables for respecifying categorical variables is also very popular. Dummy variable is a variable which usually takes numerical values based on the corresponding category in the original variable. For example, a group of people is divided into smokers and non-smokers. Scale transformation. Scale transformation is done to ensure the comparability with other scales or to make the data suitable for analysis. Different type of characteristic are measured on different scales. For example, attitude variables are measured on continuous scale, lifestyle are usually measured on a 5-point Likert scale. So the variables which are measured on different scales cannot be compared. A common transformation is subtracting all the values of a characteristic by corresponding mean and dividing by corresponding standard deviation. Problems in preparation process. We can take up the following two problems of processing the data for analytical purposes. The problem concerning don't know or DK responses. While processing the data, the researcher often comes across some responses that are difficult to handle. One category of such responses may be don't know responses or simply DK response. When the DK response group is small, it is of little significance. But when it is relatively big, it becomes a matter of major concern, in which case the question arises. Is the question which elicited DK response useless? The answer depends on 2 points, viz. The respondent actually may not know the answer, or the researcher may fail in obtaining the appropriate information. In the first case, the concerned question is said to be alright and DK response is taken as legitimate DK response. But in the second case, DK response is more likely to be a failure of the questioning process. How DK responses are to be dealt with by researchers. The best way is to design better type of questions. Good rapport of interviewers with respondents will result in minimizing DK responses. But about the DK responses that have already taken place. One way to tackle this issue is to estimate the allocation of DK answers from other data in the questionnaire. The other ways is to keep DK responses as a separate category in tabulation, where we can consider it as a separate reply category if DK responses happen to be legitimate, otherwise we would let the reader make his own decision. Yet another way is to assume that DK responses occur more or less randomly, and as such we may distribute them among the other answer in the ratio in which the latter have occurred. Similar results will be achieved if all DK replies are excluded from tabulation in the 2 without inflating the actual number of other responses. The problem of use of percentages. Percentages are often used in data presentation, for they simplify numbers, reducing all of them to a 0 to 100 range. Through the use of percentages, the data are reduced in a standard form with base equal to 100, which fact facilitates relative comparisons. While using percentages, the following rules should be kept in view by researchers. 1. 2 or more percentages must not be averaged unless each is weighted by the group size from which it has been derived. 2. Use of too large percentages should be avoided, since a large percentage is difficult to understand and tends to confuse, defeating the very purpose for which percentage are used. 3. Percentage hide the base from which they have been computed. If this is not kept in view, the real differences may not be correctly read. 4. While using percentages, the following rules should be kept in view by researchers. 1. 2 or more percentages must not be averaged unless each is weighted by the group size from which it has been derived. 2. Use of too large percentages should be avoided, since a large percentage is difficult to understand and tends to confuse, defeating the very purpose for which percentage are used. 3. Percentage hide the base from which they have been computed. If this is not kept in view, the real differences may not be correctly read. 4. Percentage decrease can never exceed 100%, and as such, for calculating the percentage of decrease, the higher figure should invariably be taken as the base. 5. Percentages should generally be worked out in the direction of the causal factor in case of two-dimension tables, and for this purpose we must select the more significant factor out of the two given factors as the causal factor. Review questions. 1. Why collected data is to be prepared and processed? 2. What is meant by data preparation process? 3. Enlist the activities coming under data preparation. 4. State the objective of data processing. 5. What is meant by questionnaire checking? 6. Why data should be edited? 7. What do you mean by coding? 8. Explain classification of data. 9. What is meant by attribute? 10. Give an example of exclusive classification. 11. How to determine frequency of each class. 12. What is meant by tabulation? 13. State principles of tabulation. 14. Explain graphical representation. 15. What is a pie chart used for? 16. What do you mean by data cleaning? 17. What is meant by data adjusting? 18. What are the components in data adjustment? 19. State problems in data preparation process. 20. How the problem of DK responses should be dealt with by a researcher. 21. How will you treat missing data? Unit 18. Data analysis. Introduction. The purpose of research is to find out something. Analysis of data helps to find out this something. Analysis of data is to be made with references to the problem at hand. Analysis, we mean the computation of certain measures or indices along with searching for patterns of relationship that exist among the data groups. In case of survey and experimental data, analysis involves estimating the values of unknown parameters of the population and testing of hypothesis for drawing inference. As stated earlier, by analysis we mean the computation of certain indices or measures along with searching of patterns of relationship that exist among the data groups. Analysis, particularly in case of survey or experimental data, involves estimating the values of unknown parameters of the population and testing of hypotheses for drawing inferences. Approaches to data analysis. Coded data can be analyzed manually or with the help of a computer. If the number of respondents is reasonably small, there are not many variables to analyze, and you are neither familiar with a relevant computer program, nor wish to learn one, you can manually analyze the data. However, manual analysis is useful only for calculating frequencies and for simple cross-tabulations. In addition, if you want to carry out statistical tests, they have to be calculated manually. However, the use of statistics depends upon your expertise and desire or need to communicate the findings in a certain way. Be aware that manual analysis is extremely time-consuming. The easiest way to analyze data manually is to code it directly onto large graph paper in columns in the same way as you would enter it into a computer. On the graph paper you do not need to worry about the column number. Detailed headings can be used or question numbers can be written on each column to code information about the question. Types of analysis. Analysis of data can be categorized as descriptive analysis and inferential analysis. Descriptive analysis deals with the study of variables. When the study is of one variable, it is called unidimensional analysis, and when the study is about two variables, it is called bivariate analysis. If it is about more than two variables, it is called multivariate analysis. In descriptive analysis, we work out various measures which will show size and shape of a distribution and also measures the degree of the relationship between two or more variables. Descriptive analysis, like correlation analysis, causal analysis, regression analysis, etc., deal with relationship between two or more variables for determining the amount of correlation or association between two or more variables. Causal analysis is concerned with the study of how one or more variables affect changes in another variable. It assesses functional relationship existing between the variables. This analysis can be termed as correlation analysis. It is important in experimental researchers, but in social and business researchers correlation analysis is relatively more important. Multivariate analysis deals with simultaneously more than two variables. Multiple regression analysis, multivariate analysis of variance, canonical analysis, etc., or various multivariate analysis techniques. In multiple regression analysis, the researcher has one dependent variable and two or more independent variables. This analysis facilitates prediction of the value of dependent variable based on its relation with all the concerned independent variables. When the researcher has a single dependent variable that cannot be measured but can be classified into two or more groups on the basis of some attribute, we have multiple discriminant analysis. With the help of this analysis we can predict an entity's possibility of belonging to a particular group based on several predictor variables. In multivariate analysis of variance, we find out the ratio between within group variance and among group variance. Canonical analysis facilitates simultaneous prediction of a set of dependent variables. This analysis can be used in the case of both measurable and non-measurable variables. Correlation analysis and causal analysis are closely related. Correlation analysis studies the joint variation of two or more variables for determining the amount of correlation between two or more variables. Causal analysis is concerned with the study of how one or more variables affect changes in another variable. It is thus a study of functional relationships existing between two or more variables. This analysis can be termed as regression analysis. Causal analysis is considered relatively more important in experimental researches, whereas in most social and business researches our interest lies in understanding and controlling relationships between variables than with determining causes per se, and as such we consider correlation analysis as relatively more important. Multiple regression analysis is adopted when the researcher has one dependent variable which is presumed to be a function of two or more independent variables. The objective of this analysis is to make a prediction about the dependent variable based on its covariance with all the concerned independent variables. Multiple discriminant analysis is appropriate when the researcher has a single dependent variable that cannot be measured, but can be classified into two or more groups on the basis of some attribute. The object of this analysis happened to be to predict an entry's possibility of belonging to a particular group based on several predictor variables. Multivariate analysis variance, or multi-ANOVA. This analysis is an extension of two-way ANOVA, wherein the ratio of among group variance to within group variance is worked out on a set of variables. Canonical analysis. This analysis can be used in case of both measurable and non-measurable variables for the purpose of simultaneously predicting a set of dependent variables from their joint covariance with a set of independent variables. Inferential analysis is concerned with the various tests of significance for testing hypothesis in order to determine with what validity data can be said to indicate some conclusion or conclusions. It is also concerned with the estimation of population values. It is mainly on the basis of inferential analysis that the task of interpretation, i.e. the task of drawing inferences and conclusions, is performed. Statistics in research. The role of statistics in research is to function as a tool in designing research, analyzing its data and drawing conclusion therefrom. Most research studies result in a large volume of raw data which must be suitably reduced so that the same can be read easily and for further analysis. Clearly the science of statistics cannot be ignored by any research worker, even though he may not have occasion to use statistical methods in all their details and ramifications. Classification and tabulation as stated earlier achieve this objective to some extent, but we have to go a step further and develop certain indices or measures to summarize the collected classified data. Only after this we can adopt the process of generalization from small groups, i.e. samples, to population. In fact, there are two major areas of statistics, viz. descriptive statistics and inferential statistics. Descriptive statistics concern the development of certain indices from the raw data, wherein inferential statistics concern with the process of generalization. Inferential statistics are also known as sampling statistics and are mainly concerned with two major types of problems. I. The estimation of population parameters, and E. The testing of statistical hypotheses. Important statistical measures that are used to summarize the survey or research data are: 1. Measures of central tendency or statistical averages. 2. Measures of dispersion. 3. Measures of asymmetry, skewness. 4. Measures of relationship. And 5. Other measures. Among the measures of central tendency, the three most important ones are the arithmetic average or mean, median and mode. Geometric mean and harmonic mean are also sometimes used. From among the measures of dispersion, variance, and square root, the standard deviation are the most often used measures. Other measures such as mean deviation, range, etc. are also used. For comparison purpose, we are mostly the coefficient of standard deviation or the coefficient of variation. In respect of the measures of skewness and kurtosis, we mostly use the first measure of skewness, based on quartiles or on the methods of moments, or also used sometimes. Kurtosis is also used to measure the peakness of the curve of the frequency distribution. Amongst the measures of relationship, Carl-Pearson's coefficient of correlation is the frequently used measures in case of statistics of variables, whereas Yule's coefficient of association is used in case of statistics of attributes. Multiple correlation coefficient, partial correlation coefficient, regression analysis, etc., are other important measures often used by a researcher. Index numbers, analysis of time series, coefficient of contingency, etc., or other measures that may as well be used by a researcher, depending upon the nature of the problem under study. We present below a brief outline of some important measures, out of the above listed measures often used in the context of research studies. Role of computers in data analysis. Knowledge of computers and the relevant programs is extremely important and ultimately saves time. Data can be analyzed with the help of computers even for qualitative and descriptive information. Computers primarily help to save labor in manual data analysis and in the calculation of descriptive and inferential statistics. Computers are tools that increase your speed, handle complicated statistical and mathematical procedures, print the report, display the analyzed data and present them graphically. They are designed to perform extremely complicated procedures, which otherwise could be very time-consuming, in an extremely short time. While computers are designed to support computing and analyzing research activities, a good understanding of them is required to be able to benefit from them. The time spent in learning about computers is ultimately worthwhile, whether you classify yourself as a qualitative or quantitative researcher. Tools for statistical analysis. There are two major areas of statistics related with research: descriptive statistics and other is inferential statistics. Descriptive statistics is related with the development of certain indices from the collected data. Inferential statistics or sampling statistic is related with the process of testing a hypothesis and generalization. The following are the important statistical tools used for summarizing the research data. Measures of the central tendency or averages, measures of the dispersion. Measures of the skewness. Measures of the relationship. Other measures. Measures of the central tendency. Measures of the central value or typical value of the entire group of data. It describes the characteristics of entire mass of data. It is the average value of the entire data. In other words, it is the single value that describes the characteristics of the entire group. There are 5 types of averages, namely mean, median, mode, geometric mean and harmonic mean. Mean. Mean is known as arithmetic mean. It is the most common measures of central tendency. Its value is obtained by adding all items and by dividing this by the total number of items. Mean x equals x. And in shortcut method, the concept of assumed mean is used to find out mean. Mean is the simplest measurement of tendency and it is widely used. It is relatively stable measure of tendency. It is also relatively reliable in the sense that it does vary too much as the repeated samples are from one and the same population. It has limitations also. It is unduly affected by extreme items. That is very large and small items. Median. Median is the middle value in the distribution when it is arranged in descending or ascending order. It may be defined as the value of that item which divides the series into equal parts. One half contains values greater than it and the other half contains value less than it. Therefore the series is to be arranged in ascending or descending order. Median equals size of n plus 1 th item. 2 median is not frequently used in sampling theory. Mode. It is the most common item of a series. Mode is the positional average and it is not affected by the values of extreme items. Mode is defined as the value of the variable which occurs most frequently in distribution. The chief feature of the mode is that it is the size of that item which has the maximum frequency and is also affected by the frequencies of the neighboring items. It is particularly useful in study of popular sizes. Geometric mean. The geometric mean of n positive figures is the nth root of their products. The geometric mean is the obtained by multiplying together all the values of the series and then calculating the root of their product corresponding to the number of items in the group. Geometric mean equals where n equals number of items in x1, x2 or various values. It is often used in the preparation of the index numbers or when we deal in ratios. It cannot be computed if any item in the series is negative or 0. Harmonic mean. It is special type measure of central tendency used to solve special type of problems. It is the reciprocal of values of various items in the variable. HM equals n. x1, x2, xn. Where is x1, x2, xn refer to the various values in the observations. It has limited application. It gives largest weight to the smallest item and smallest item to the largest item. From the above, it is clear that there are large numbers of averages. The selection of the particular statistical average depends 1 plus 1 plus 1. Upon the nature, type and objectively of the research. All averages are not suitable for all studies. Measures of dispersion. The measures of central tendency indicate the central tendency of a frequency distribution in the form of an average. These averages tell something about the general level of magnitude of the distribution, but it does not show anything further about the distribution. Especially it fails to give an idea about the dispersion of variables. In order to measure dispersion, statistical device names measures of dispersion is to be calculated. According to Spiegel, the degree to which numerical data tend to spread about an average value is called the variation or dispersion of data. The variation measures is used to test the representative character of an average. The following are the important measures of dispersion. Range. It is the simplest measure of dispersion. Its measure depends upon the extreme items and not on all items. It is defined as the difference between the highest value and the lowest values. In a series, it gives an idea about the variability very quickly. The limitation is that the range is affected greatly by fluctuation of sampling. It is not considered as an appropriate measure in research studies. Mean deviation. The mean deviation is a measure of dispersion based on all items within a distribution. It is the arithmetic mean of the deviation of series computed from any measure of control tendency. It is the average of the absolute differences of values of items from an average. It is worked out as under. Mean deviation equals. Where d equals sum of deviations and n equals number of items. Mean deviation is calculated by any measure of central tendency. It is an absolute figure. To compare variation among different series which are expressed in the same or different units, the relative mean deviation is required. The relative mean deviation is known as coefficient of mean deviation. The coefficient of mean deviation can be obtained by dividing mean by the average used for calculating mean deviation. Coefficient of mean deviation equals mean deviation. Mean or median or mode. Standard deviation. Carl Pearson introduced the concept of standard deviation in 1893. It is the most important measure of dispersion and it is widely used in many statistical formulae. It is commonly denoted by the symbol sigma. It is defined as the positive square root of the arithmetic mean of the squares of the deviation of the given observation from an arithmetic mean. The following formula is to be applied to find standard type equation here deviation. Coefficient of standard deviation. If we divide the standard deviation by the arithmetic average of the series, we will get coefficient of standard deviation. It is relative measures which is used to compare it with similar measure of other series. Coefficient of variation. If we multiply the coefficient of standard deviation with 100, we will get coefficient of variation. The square of the standard deviation is known as variance. It is considered as the best appropriate method of comparing the variability of two or more distribution. The standard deviation along with several other related measure like variance, coefficient variation etc. are used mostly in research studies. It is possible for further algebraic treatment. It is less affected by the fluctuations of sampling. It is the basis for measuring the coefficient of correlation, sampling and statistical inferences. The main limitation of this method is that it is an absolute measure of variability, so it cannot be used for the purpose of comparison. Measures of skewness. The measures of dispersion give an idea about the spread of the observation about the central tendency of items. The measures of dispersion give an idea about the spread of the observation about the central tendency do not indicate whether the distribution is symmetric or not. We know that frequency distribution differ widely in their nature and composition. Even then they may have central tendencies and the dispersion same. When the items in series are dispersed in even fashion, the frequency curve representing the distribution will be symmetrical. If the distribution of the items in a series happen to be symmetrical, curve of the distribution will be normal. It is known as normal curve. In a symmetrical distribution the items show a perfect balance on either side of the central tendency. In this case the mean, median and mode will be the same. There is no skewness. If the distribution is asymmetrical, it shows that it has skewness. So, skewness is a measure of asymmetry. It shows the manner in which the item are clustered around the average. The measure of skewness helps us to determine the nature and extent of concentration of the observations towards higher or lower values of the variables. It also helps to measure direction. The following formula can be used to find measure of skewness. Correlation. Measures of central tendency, measures of dispersion, skewness etc. are used in the context of unvariate population. If we have bivariate population it is used for finding out the relationship and cause and effect relationship between variables. Correlation technique is used to know the correlation between the two or more variables. Regression techniques are used to know the cause and effect relationship between the two variables. If there is multivariate population, coefficient of partial correlation, coefficient of multiple variation, multiple regression etc. are used for study. Scatter diagram method. It is the simplest device for ascertaining the relationship between two variables. Under this method, the values are plotted simply in a graph paper in dots. By looking the scatter of dots, we can form an idea as to whether the variables are related or not. The greater the scatter of the plotted points, lesser is the relationship between the variables. The more closely points come to a straight line, and then it indicates that there is high degree of relationship. If all the points lie on a straight line from the lower left-hand corner to the upper right-hand corner, the correlation is said to be perfectly positive correlation r equals -1. Graphic method. Under this method the individual values of the two variables are plotted on a graph paper. The points are then joined together. It will provide two curves. That is one for variable and other for y variable. If both curves are running parallel, we can conclude that there is perfect positive correlation. If they are running in opposite directions, we can conclude that there is a perfect negative correlation. This method does not give the idea about the degree of correlation between them. Hence this method is treated as rough method for studying correlation. Coefficient of correlation. Carl Pearson's coefficient correlation is the most popular method used to find out the coefficient of correlation. It is also known as rank correlations. Under shortcut method the coefficient of correlation can be found out by using the following formula where the assumed mean is taken. Where x, y equals deviations from actual means. When deviations are taken from assumed means. Where dx, di equals deviations from assumed means. The value of y lies between +1. Positive values of r indicate positive correlation between two variables and negative values, r indicates negative correlation. When r indicates 0 there is no relationship between the two variables. The method gives a numerical measure of correlation. Great care must be taken while interpreting value of this because it is very often misinterpreted. Regression analysis. Correlation analysis helps to determine the relationship between two variables. Regression technique is used to estimate or predict the value of one variable, dependent variable, with the help of another variable, independent variable. Regression is the measure which indicates the average relationship between two or more variables in terms of original units of data. The line describing the average relationship between two variables is known as line of regression or estimating line or regression line. The direction of the line indicates the nature of correlation. If the lines are sloping upwards from left to right, it is positive, and if they are sloping downwards it is negative. If the lines coincide, there is perfect correlation. This technique is useful for prediction in business. Regression equations. As there are two regression lines, there are two regression equations. For the two variables x and y there are two regression equations, namely regression equation of x on y and regression equations y and x, where is plus correlation between variables, the regression lines will coincide. That means it is one line. If regression lines are farther, the lesser is the degree of correlation, and near the regression lines, correlation is greater. Multiple correlations and multiple regressions. Or more than two independent variables, multiple correlation technique is used to describe relationship. The coefficient of multiple correlations serves as a measure of the degree of correlations between one variable taken as a dependent variable and a group of other variables taken as independent variables. It has many limitations. It is based on the assumption that the relationship between the variables is linear and the effects of independent variable on the dependent variables are separate, addictive and distinct. Partial correlation is the correlation between one dependent variable with other independent variable, putting all other variables constant. It helps to measure the relationship between two variables in such a way that the effects of other related variables are eliminated. That means the relationship between a dependent variable and a particular independent variable is studied by putting the other variables as constant. Other tools of analysis: index numbers. When series of data are expressed in different units, we cannot use averages to compare them. In such cases we want to depend on certain other measures through which the figures are reduced to a common base. One such method is to convert series into a series of index numbers. An index number may be described as a specialized average designed to measure the change in a group of related variables over a period of time. So these are devices for measuring the differences in the magnitude of a group of related variables. Changes in the various economic and business phenomena can be measured economic and compared with the help of index number. It may use to find out the change in price level over a period of time. Price movements can be studied to know its cause or effect on the economy. Index numbers may measure cost of living index of different classes of people. Index numbers have limitations. It is often difficult to take into account of the changes in the quality of products. Chances of error may remain at one point or the other while constructing an index number. Time series analysis. It is an arrangement of statistical data in accordance with the time of occurrence or in a chronological order. The numerical data which are collected from different points of time is known as time series. This technique has an important role in economics, statistics and commerce, e.g. daily sales in a shop, population growth of 10 years, etc. There are 4 types of variations which are the components of the time series. Secular trend or long-term movement, seasonal variation, cyclical fluctuation, and random fluctuation. Secular trend is the long-term trend which requires 15 to 20 years. There are upward trend and downward trend. Seasonal variation is a variation which occurs with some degree of regularity within a specified period of time of 1 year or shorter. The seasonal variations occur due to change in climate and custom, habits of the people, etc. Cyclical fluctuations are the fluctuations occurs over a long period of time. It is up and down, e.g. depression period, then boom period. Random variation is the irregular variations occurs due to unforeseen and unpredictable events like flood, drought, lockouts, etc. Generally 4 methods are used to measure these trends, namely graphic method, semi-average method, moving average method, and method of least squares. The analysis of time series is done to understand the dynamic conditions to achieve short-term and long-term goals of business enterprises. The management can predict the future patterns on the basis of the past figures. The knowledge of the seasonal variations is very much useful to take decisions related with production, inventory, purchase, etc. By studying cyclical fluctuation, the policy of the business can be formulated. So it is a power tool in the hands of business researchers and analysis. Growth rates. Estimates of trend are required for almost research studies. It has a considerable significance related to academicians and policymakers. For example, trend in deposits, computation of growth rate is the most important method used for this purpose. The entire series of observation is used for the purpose of finding growth rate. There are 2 common functional forms used for computations of growth rates with the help of least square method. Linear growth rate. The following equation is used. Yt equals a plus bt. Yt equals the value of the variables in the period t for which the growth rate is to be estimated. That t equals 1, 2, n. A and b are constant to be estimated. This formula assumes that the change in y is a constant linear rate of b units per year, and this rate does not depend on the value of y in the previous year or any other factor. Compound growth rate. Linear rate of growth is not applicable when the growth in any period is not independent of the value of the variable in the precious period. In this case, the compound growth rate is applied. Inferential analysis. The purpose of sampling is to estimate some characteristic of the population from which a sample is selected. In almost all fields, the statistical inquiry deals with drawing of conclusions related with a population from a sample selected from it. Statistical inference is the process by which we draw a conclusion about some measure of population on the basis of a sample value. The statistical inference or inferential analysis can be classified into 2: test of hypothesis and estimation of population parameters. Parameters and statistics. Parameters include the statistical constants of population like mean, variance, coefficient, correlation, R, etc. The statistical constants for the sample drawn from the population like mean, variance, correlation, coefficient, R, proportion, P, etc. are known as statistic. In other terms, parameters are the functions of the population values and statistic are the functions of sample observations. A sampling investigation produces a result which has to be compared with the one expected with on the basis of population parameter. Testing of hypothesis. Hypothesis is considered as the most important instrument in research. Hypothesis is a tentative conclusion logically drawn concerning any parameter of the population. In other words, a hypothesis is an assumption or some assumption to be proved or disapproved. For example, the mean height of students is 65 inches. Features of hypothesis. Hypothesis possesses the following features. It should be capable of being tested. It should be capable of being terms. It should state the relationship between variables. It must be specific. It should be consistent with known facts. Steps in testing hypothesis. The following steps are to be taken to test the hypothesis. State the problem. Set up a hypothesis. Decide a test statistic. Select a level of significance. Calculate the value of the test statistic. Obtain the table value. Make a decision to accept or reject hypothesis. Testing for means. It frequently happens that samples are from 2 different sources and it is required to know whether there is any significant difference in their means. We also want to know when the difference is due to chance, whether the samples belong to the same population. Hence the problem is I to test the equality of the population mean and sample mean, E to test the significance of the difference between 2 independent sample means. For testing population mean or sample means, compute Z value, if the sample is large i.e., 30 or more and compare with Z table value. If the sample size is less than 30, compute T value, and compare the computed value of T with the tabulated value of T for the degree of freedom. The desired level of significance is usually 1% or 5%, we accept null hypothesis when the calculated value is less than table value and vice versa. Comparison of sample mean with population mean. Problem 1. A company makes bus tires. Their lives are normally distributed with a mean of 80,000 kms and standard deviation 6,000 kms. A change in the production process is believed to result in a better product. A test samples of 64 new tires has a mean life of 82,400 kms. Can you conclude that the new product is significantly better than the current one? Answer. Null hypothesis H equals there is no significant difference between population mean and sample mean. At 0.05 level of significance, the critical table value of Z is 1.96. The computed value of Z is plus 1.6, which is less than critical value, and falls in the acceptance region. Thus we accept null hypothesis. The difference is not significant. Hence we conclude that the new tires are not better than the currently one. Problem 2. Samples of 121 wooden rods are drawn from a large number of wooden rods, whose length are normally distributed with mean 6 feet. The standard deviation is 1.2 feet. If the sample mean is 6, 4 can the sample be regarded as a truly random sample? Answer. Sample is large, so use Z-test. Apply Z-test. Number of sample. Null hypothesis H equals there is no significant differences between population mean and sampling mean equals 6 feet. At 0.05 level of significance, the critical value is per table value of Z equals 1.96. The computed value is plus 3.67. It falls in the rejection region. Thus we reject the null hypothesis that there is no difference between population mean and sample mean. The difference is significant. Hence the sample cannot be regarded as truly random sample. Problem 3. A talcum powder manufacturing company was distributing a particular brand of talcum powder through a large number of retail shops. Before a heavy advertisement campaign, the mean sales per week per shop were 70 dozens. After the campaign, a sample of 10 shops was taken and the mean sales were found to be 74 dozens with standard deviation of 8. Can you consider the advertisement effective? Answer. Null hypothesis equals there is no significant difference between the mean sales. The advertisement is not effective. No. A sample size is less than 30, so apply T-test. For 9 degree of freedom at 5% level of significance, the table value of t is 2.26. The calculated value of t 1.49 is less than the table value. So it falls in acceptance region. Hence there is no significant difference between mean samples, and the income in sales can be attributed to fluctuations of sampling. We conclude that the advertisement is not effective in increasing sales. Comparison of two sample means. Problem 4. A and B companies manufacture electronic bulbs and gave the following results. Mean life of the two bulbs, in hours of 1300 and 1248 respectively. Number of bulbs used for test purposes are 100 each. Standard deviations for A is 82 and for B is 93 respectively. Using the standard error of the difference between means, state whether there is any significant difference in the mean life of the two makes. Answer. Let Ho equals no significant difference between the mean lives of the bulbs. Test statistic for large samples. Z-test calculated value is 4.19. At 0.05 level of significance, the difference is significant for a two-rail test because Z-table value is 1.96. Thus we reject the null hypothesis, and conclude that the two population means are not same. In other words, there is a significant difference in the mean life of the two makers. Analysis of variance and covariance. Z-test T-test is used to test the hypothesis of equality between two sample means. F-test is used to verify the hypothesis of equality between two variances. The same test is extended towards the test of hypothesis of equality amongst several means. Analysis of variance ANOVA is an important statistical tool related with researches in the field of economics, biology, education, psychology, sociology, business and industries, and several other disciplines. If there are only two groups, the researcher can apply T-test to determine the significance. Even if there are three groups of sample results, they can be compared pair by pair by employing T-test. But there are several groups, it is difficult to compare the sample statistics pair by pair. In these cases, analysis of variance is only the tool that can be employed to test the null hypothesis that the samples are drawn from the same population. Analysis of variance is only the tool that can be employed to test the null hypothesis that the samples are drawn from the same population. This technique is used when multiple sample cases are involved in our studies. It can be used to draw inferences about whether the samples have been drawn from population having the same mean. Assumptions in ANOVA. This technique is based on three important assumptions. The distribution of individual values in each group is assumed to have normal shape curve. The variance of individuals' value within each group is assumed to be the same. That the individuals sample being observed have been selected randomly from the population. There are two techniques of analysis of variance, one-way classification and two-way classification. One-way classification. In one-way classification, data are classified on the basis on a single criterion and the data is presented either horizontally or vertically. In one-way ANOVA, following are the important steps. Calculate mean of each sample. Calculate the grand average. Take the difference between the means of the various samples and the grand average. Square these deviations and find the sum of squares between the samples SSC. Divide SSC by degree of freedom. We will get mean square between samples MSC. Degree of freedom equals number of samples minus 1. Calculate variance within samples. Calculate mean value of each sample. Take the deviations of various items in a sample from the mean values of the respective samples. Square these deviations. Then we will get the sum of squares within the samples SSE. Divide the sum of square with the degree of freedom. That will give mean square within samples MSE. Degree of freedom equals number of observations, number of samples. Calculate the value of F. It can be found out by using the following formula. F equals mean square between samples, mean square within samples. F indicates the variance ratio. F value is compared with the critical value or table value of F distribution. If the computed value is greater than the critical value, we shall reject the hypothesis that all the groups are drawn from the common population. If the compound value is smaller, accept the null hypothesis. Analysis of variance, two-way classification. In this case, the data is classified according to two different criteria or factors. The procedure for calculation of F under two-way classification is summarized in the table given below. Between columns SSC C1 MSC equals SSC C1, between rows SSR R1 MSR equals SSR R1, residual SSC C1 R1 MSE equals SSE R1 C1, total SST N1. ANOVA table. Source of variation, sum of squares df mean square. SSC indicates the sum of squares between columns. MSC indicates mean square between columns. SSR denotes sum of squares between rows. MSR indicates mean square between rows. SSE indicates the sum of squares for the residual. MSE denotes the mean square within residuals. SST is the total sum of squares. In problems which involve two-way classifications, residual is a measuring rod to test significances. It represents the extent of variation due to forces called chance. Variance between columns and variance between rows are computed as above and compared with radical variance, and two F values are obtained. These two F values are compared with concerned F table values, and the significance of difference decided. Residual equals total sum of squares, sum of squared between columns and sum of squares between rows. Problem 6. The CalCut Traders wishes to test whether its three salesmen named James, Raghu and Bashir tend to make sales of the same size or whether they differ in their selling ability as measured by the average size of their sales. During the last week, there have been 14 sales calls. James made 5 calls, Raghu made 4 calls and Bashir have made 5 calls. The following is the weekly sales record of the 3 salesmen. James Rs Raghu Rs Bashir Rs 300 octillion 600 septillion 700 sextillion 400 quintillion 300 quadrillion 300 trillion 300 billion 300 million 400,000 500 400 600 500. Perform the analysis of variance and conclude whether the 3 salesmen differ between themselves in sales efficiency. Answer. Hypothesis. There is no differences between the selling ability of 3 salesmen. This is one-way analysis of variance. Coding method is applied to simplify data. 100 is taken as common factor. Calculated F value equals 1.83. The table value of F at 5% level of significance for 2.11 degree of freedom is 3.98. The calculated value 1.83 is less than table value, so we accept the null hypothesis. We conclude that there is no significant difference among salesmen in their ability measured in terms of mean sales per week. Non-parametric tests. While applying the parametric test like T, F and Z test, it is assumed that samples are drawn from normally distributed population. It is also assumed that mean, standard deviation or proportion can be derived from sample data and can be used for estimating the corresponding population parameter. In certain situations it is not possible to make any rigid assumption about the distribution of the population from which samples are being drawn. This limitation has led to the development of non-parametric tests. It is also known as distribution-free methods. So while applying non-parametric tests, no assumption about population parameter of the populations or populations from which samples are drawn is made. Chi-square test is the most widely used test under this category. A large variety of non-parametric tests are developed by different statisticians. It includes sign tests, Fisher-Irwin tests, Wilcoxon-Mann-Whitney test, or U-test, Kruskal-Wallis test, or H-test, and Spearman's correlation. Chi-square test. Chi-square test is one of the important tests developed to test hypothesis. It is a non-parametric test. This test is first used by Carl Pearson in the year 1900. We want to ascertain the frequency of events falling in specified categories in a number of business problems. For example, in marketing research we count the number of people who prefer a particular brand of talcum powder. Chi-square test is applied to such frequencies of occurrences as against the expected ones without referring the population parameters. It is frequently used for testing hypotheses concerning the differences between a set of observed frequencies of a sample and corresponding set of expected or theoretical frequencies. In other words, it is a test statistic. Which measures the discrepancy between observed or actual frequencies and their corresponding expected frequencies is called the chi-square test X2. X2 equals OE2 where O equals observed frequencies, E equals expected frequencies. Degree of freedom equals N1 if observations are given in a series. Degree of freedom. The calculated value 1.83 is less than table value, so we accept the null hypothesis. We conclude that there is no significant difference among salesmen in their ability measured in terms of mean sales per week. Non-parametric tests. While applying the parametric test like T, F and Z test, it is assumed that samples are drawn from normally distributed population. It is also assumed that mean, standard deviation or proportion can be derived from sample data and can be used for estimating the corresponding population parameter. In certain situations it is not possible to make any rigid assumption about the distribution of the population from which samples are being drawn. This limitation has led to the development of non-parametric tests. It is also known as distribution-free methods. So while applying non-parametric tests, no assumption about population parameter of the populations or populations from which samples are drawn is made. Chi-square test is the most widely used test under this category. A large variety of non-parametric tests are developed by different statisticians. Sign tests, Fisher-Irwin tests, Wilcoxon-Mann-Whitney test, or U-test, Kruskal-Wallis test, or H-test, and Spearman's correlation. Chi-square test. Chi-square test is one of the important tests developed to test hypothesis. It is a non-parametric test. This test is first used by Carl Pearson in the year 1900. We want to ascertain the frequency of events falling in specified categories in a number of business problems. For example, in marketing research we count the number of people who prefer a particular brand of talcum powder. Chi-square test is applied to such frequencies of occurrences as against the expected ones without referring the population parameters. It is frequently used for testing hypotheses concerning the differences between a set of observed frequencies of a sample and corresponding set of expected or theoretical frequencies. In other words, it is a test statistic which measures the discrepancy between observed or actual frequencies and their corresponding expected frequencies is called the chi-square test X2. X2 equals OE2 where O equals observed frequencies, E equals expected frequencies. Degree of freedom equals N1 if observations are given in a series. Degree of freedom equals R1, C1 if a two-way matrix is given. Steps in chi-square test. The following steps are required to determine the value of the chi-square test. Form null hypothesis that there is no significant difference. Consider given frequencies as observed frequencies. Calculate expected frequencies. Take the differences between observed and expected frequencies. Obtain the square of the differences. Divide DE2 with the expected frequency and get chi-square values. Obtain total X2 value by summating calculated values. Compare the calculated value with chi-square table value. The greater the discrepancy between observed and expected frequencies, the greater shall be the value of X2. The calculated value of X2 is compared with the table value of X2 for a given degree of freedom at a certain specified level of significance. 5% level of significance, the calculated value of X2 is more than the table value of X2. The difference between theory and observation is considered as significant. That means it could not have arisen due to fluctuation of simple sampling. The value of X2 is always positive. Problem 5. The table given below depicts the data obtained during an epidemic of cholera. Attack total inoculated 21,479,500, not inoculated 1751, 1325, 1500, total 196, 1804, 2000. T effectiveness of inoculation in preventing the attack of cholera. Answer. Ho equals the inoculation is not effective in preventing the attack of cholera. That is, inoculation and attack is independent. This hypothesis, the expected frequency corresponding to the number of persons inoculated and attached would be equals. Expectation of AB equals A x B. N. Here A equals total of a column. B equals total of a row. AB equals grand total. Therefore A equals 196, B equals 500, AB equals 2000, AB equals 196 x 500 equals 49. On the basis of the above value. 2000 we can find other values. Attacked not attacked total inoculated 49,451,500, not inoculated 147, 1353, 1500, total 196, 1804, 2000. Now put the observed frequencies and expected frequencies together and find chi-square values. Equals R1, C1 equals 2 to 1, 2 to 1 equals 1 when D equals 1, X2 0.05 equals 3.84. The calculated value of X2 is higher than the table value and hence the result of the experiment does not support the hypothesis. We therefore conclude that the inoculation is effective in preventing the attack of cholera. Mann-Whitney U-test and Wilcoxon test. It is a most useful test to see whether the values in two samples differ in size. It resembles the median test in scope, but it is much more sensitive. In fact, for large numbers it is almost as sensitive as the two-sample student t-tests. For small numbers with unknown distributions this test is even more sensitive than the student t-test. As it is only on rare occasions that we do know that values are normal distributed, this test is to be preferred over the student t-test. In this test, state ranked. It is used when only populations are involved. All the observations in the two samples are to be ranked. L hypothesis is fixed that there is no differences between the qualities of two samples. The statistic U is calculated from the sum of the rank in sample 1 and sample 2. McNamara test. McNamara's test is generally used when the data consists of paired observations of tables. This non-parametric test uses matched pairs of labels A, B. It determines whether the proportion of on labels is equal for both members. It is a very good test when only nominal data are available. The sign test. Sign test is a parametric test that may be of use when it is only necessary or possible to know if observed differences between two conditions are significant. That is to say, with appropriate use of the sign test, it would be possible to determine if X is really more than Y, or however the conditions are arranged. The sign test is structured so that plus and sign are used to denote change in magnitude, as opposed to any attempt at quantitative measurement. Factor analysis. Factor analysis is by far the most often used multivariate technique of research studies, especially pertaining to social and behavioral sciences. It is a technique applicable when there is a systematic interdependence among a set of observed or manifest variables and the researcher is interested in finding out something more fundamental or latent which creates this commonality. Hence, we might have data, say about an individual's income, education, occupation and dwelling area and want to infer from these some factor, such as social class, which summarizes the commonality of all the said four variables. The technique used for such purpose is generally described as factor analysis. Factor analysis, thus, seeks to resolve a large set of measured variables in terms of relatively few categories known as factors. This technique allows the reader to group variables into factors based on correlation between variables, and the factors to derive may be treated as new variables often termed as latent variables and the factors to derive by summing the values of the original variables which have been grouped into the factor. The meaning and name of such new variables is subjectively determined by the researcher. Since the factors happen to be linear combinations of data, the coordinates of each observation or variables is measured to obtain what are called factor loadings. Such factor loadings represent the correlation between the particular variable and the factor, and are usually placed in a matrix of correlation between the variable and the factors. Mathematical basis of factor analysis. Mathematical basis of factor analysis concerns a data matrix, also termed as score matrix, symbolized as S. A matrix contains the scores of n persons of k measures. Thus A1 is the score of person 1 on measure A, A2 is the score of person 2 on measure A, and Kn is the score of person n on measure K. The score matrix then take the form as shown following. Dissonant analysis. Dissonant analysis is a technique to discriminate between two or more manually exclusive and exhaustive groups on the basis of some explanatory variable. These groups are known a priori. When the criterion variable has two categories, the technique is known as two-group discriminant analysis. When three or more categories are involved, the technique is referred to as multiple discriminant analysis. Discriminant analysis helps the researchers who are interested to understand how consumers differ with respect to demographic and psychographic characteristic. Discriminant analysis is also used to predict the group membership. Let's use discriminant analysis to discriminate between the customers who default and who repay the loan in time, based on their age, income, assets, number of dependents and previous outstanding loan, etc. Consider the following example. Example 16.1. Suppose a company wants to determine if one of its new product, a new and improved digital camera, will be commercially successful or not. The company wants to distinguish the purchasers from non-purchasers. The company makes a panel of 10 potential purchasers and divides the rating scales on three characteristics: durability, performance and style. Panel is asked to give the digital camera rating from 1 to 10 on these three scales. After the product was evaluated, they are asked their buying intention, would purchase or would not purchase. 5 said that they would purchase the digital camera and the other 5 said that they would not purchase it. Such an analysis may lead to a conclusion based on the discrimination of the purchasers and non-purchasers. Cluster analysis. The purpose of cluster analysis is to divide a large group of subjects or observations, like customers or products, into smaller groups such that the observations within each group are dissimilar or far away. These smaller groups are called as clusters. Resulting clusters exhibit high internal within cluster homogeneity and high external between clusters heterogeneity. Cluster analysis is an interdependence technique and makes no distinction between dependent, steady, and independent explanatory variables. Not that, we do not combine the variables here as done in factor analysis. In factor analysis, we reduce number of variables by grouping them into smaller set of factors, while in cluster analysis we reduce number of observations by grouping them into smaller set of clusters. Number of groups or clusters is not known in advance, they are natural clusters as suggested by the data. Main applications of cluster analysis are segmenting the market and determining target markets, product positioning and new product development, and selecting test markets. Some applications of cluster analysis are illustrated below. Identifying people with similar patterns of past purchases so that you can tailor your marketing strategies. Clubbing television shows into homogeneous categories based on viewer characteristics, market segmentation. Examining patients with a diagnosis of swine flu to determine if distinct subgroups can be identified based on a symptom checklist and results from pathological tests. In cluster analysis, we group the observations based on a particular set of variables. These variables affect the clusters obtained using cluster analysis. There is no general rule of selecting the variables. We have to be careful while selecting these variables. After selecting the variables, we obtain sample observations on those variables. Path analysis. The term analysis was first introduced by the biologist Sewall Wright in 1934 in connection with decomposing the total correlation between any two variables in a causal system. The technique of path analysis is based on a series of multiple regression analysis with the added assumption of causal relationship between independent and dependent variables. This technique lays relatively heavier emphasis on the heuristic use of visual diagram, technically described as a path diagram. An illustrative path diagram showing interrelationship between father's education, father's occupation, son's education, son's first and son's present occupation can be shown. Path analysis makes use of standardized partial regression coefficients, known as beta weights, as effect coefficients. In linear additive effects are assumed, then through path analysis a simple set of questions can be built up showing how each variable depends on preceding variables. The main analysis is that any correlation coefficient between two variables, or a gross or overall measure of empirical relationship, can be decomposed into a series of separate paths of influence lending through chronologically intermediate variable to which both the correlated variables have links. The merit of path in comparison to co-relational analysis is that it makes possible the assessment of the relative influence of each antecedent or explanatory variable on the consequent or criterion variables by first making explicit the assumptions underlying the causal connections and then by elucidating the indirect effect of the explanatory variables. The used analysis technique requires the assumption that there are linear additive, symmetric relationships among a set of variables which can be measured at least on a quasi-interval scale. Each variable is regarded as determined by the variables preceding it in the path diagram, and a residual variable, defined as uncorrelated with the other variables, is postulated to account for the unexplained portion of the variance in the dependent variable. The determining variables are assumed for the analysis to be given exogenous in the model. It may again be emphasized that the main virtue of path analysis lies in making explicit the assumption underlying the causal connections and in elucidating the indirect effects due to antecedent variables of a given system. Canonical correlation. This technique was first developed by Hotelling, wherein an effort is made to simultaneously predict a set of criterion variables from their joint covariance with a set of explanatory variables. Both metric data can be used in the dependent and independent variables in such a way that linear composite of the criterion variables has a maximum correlation with the linear composite of the explanatory variables. For example, if we want to relate grade school adjustment to health and physical maturity of the child, we can then use canonical correlation analysis provided we have for each child a number of adjustment scores such as tests, teachers' ratings, parents' rating and so on, and also we have for each child a number of health and physical maturity scores such as heart rate, height, weight, index of intensity of illness and so on. The method of canonical correlation analysis is to discover factors separately in the two sets of variables such that the multiple correlation between sets of factors will be the maximum possible. Mathematically, in canonical correlation analysis, the weights of the two sets viz. A1, A2 and Y1, Y2, Y3, Yj are so determined that the variables x, A1 x1 plus A2 x2 plus AK xk plus ny equals Y1 plus Y2 Y2 plus Yj plus Y have a maximum common variance. The process of finding the weights requires factor analysis with two matrices. The resulting canonical correlation solution then gives an overall description of the presence or absence of a relationship between the two sets of variables. Latent structure analysis. This step shared both of the objectives of factor analysis viz. To extract latent factors and express relationship of observed manifest variables with these factors as their indicators and to classify a population of respondents into pure types. This type of analysis is appropriate when the variables involved in a study do not possess dependency relationship and happen to be non-metric. In above stated multivariate techniques, we may also describe the salient features of what is known as path analysis, a technique useful for decomposing the total correlation between any two variables in a causal system. Conclusion. Framed by a brief introduction of some multivariate techniques in this chapter is to motivate the reader to learn these techniques in detail. We refer the motivated learners to Johnson and Witchen, 2002. From the breakdown of multivariate techniques presented above, we may conclude that such techniques are important for they make it possible to encompass all the data from an investigation in one analysis. They in fact result in a clearer and better account of the research effort than do the piecemeal analyses of portions of data. These techniques yield more realistic probability statements in hypothesis testing and interval estimation studies. Multivariate analysis, consequently the use of multivariate techniques, is especially important in behavioral sciences and applied researchers for most of such studies involve problems in which several response variables are observed simultaneously. The common source of each individual observation generally results in dependence or correlation among the dimensions and it is this feature that distinguishes multivariate data and techniques from their unvariate prototypes. In spite of all this, multivariate techniques are expensive and involve laborious computations. As applications in the context of research studies have been accelerated only with the advent of high-speed electronic computers since 1950s. Unit 19. Interpretation of data. After collecting and analyzing the data, the researcher has to accomplish the task of drawing inferences followed by report writing. This has to be done very carefully, otherwise misleading conclusions may be drawn and the whole purpose of doing research may get vitiated. It is only through interpretation that the researcher can expose relations and processes that underlie his findings. In case of hypothesis testing studies, if hypothesis is tested and upheld several times, the researcher may arrive at generalizations. But in case the researcher had no hypothesis to start with, he would try to explain his findings on the basis of some theory. This may at times result in new questions, leading to further researches. All the information and consequential inferences may well be communicated, preferably through research report, to the consumers of research results, who may be either an individual or a group of individuals or some public or private organization. Analysis and interpretation are the integral parts of research. The important objective of analysis of data is to provide answers to the questions activated in research. Interpretation refers to drawing inferences from the collected facts after analytical study. To see William Emery interpretation has two major aspects, namely establishing continuity in research through linking the results of a given study with those of another and the establishment of some relationship with the collected data. Analysis is not complete without interpretation. So, both are interdependent. In the words of Jahada and Cook, scientific interpretation seeks the relationship between the data of study and between the study findings and other scientific knowledge. It helps the researcher to understand the conceptual principles that works underneath his findings. He can connect his findings with those of other studies having relationship with other established concepts. It is also a critical examination of the results one own analysis of data in the light of all limitations of data collection. It is through the interpretation the researcher is able to understand the real significance of his findings. Significance of interpretation. Interpretation refers to the task of drawing inferences from the collected facts after an analytical or experimental study. In fact, it is a search for broader meaning of research findings. It gains significance due to following aspects. Interpretation is the effort to establish continuity in research through linking the results of a given study with those of another. It is the establishment of some explanatory concepts. Interpretation is concerned with relationships within the collected data and the extension of study beyond the collected data as well. It is essential for the simple reason that the usefulness and utility of research findings lie in proper interpretation. It is being considered a basic components of research process because of the following reasons. It is through interpretation that the researcher can well understand the abstract principle that works beneath his findings. Through this he can link up his findings with those of other studies. The interpretation of the findings of exploratory research study often results in a hypothesis for experimental research, and as such interpretation is involved in the transition from exploratory to experimental research. Interpretation versus analysis. There is no clear-cut dividing line between analysis and interpretation. Through analysis we attempt to study the collected data and derive results, while through interpretation we draw conclusions based on the results obtained. Analysis is not complete without interpretation, and interpretation cannot proceed without analysis. So both are interdependent. Functions of interpretation. Interpretation refers to the technique of drawing inference from the collective facts and explaining the significance of those inferences after an analytical and experimental study. It is a search for broader and more abstract means of the research findings. Interpretation analyzes the abstract relations in more concrete terms and tries to unfold the reason for the existing type of relations or findings. It relates the empirical findings with theoretical principles and helps to draw a number of useful inferences from the study. The prime task of interpretation is to bring to the surface the real importance of the findings. An interpretation should explain the findings of the analysis in objective terms. It is through interpretation that a researcher can understand real significance of his findings. Through interpretation he can appreciate why the findings are and what they are. Interpretation serves a twofold purpose. First, it gives an understanding of the general factors that seem to explain what has been observed in the course of a study. Second, it provides a theoretical conception which can serve in turn as a guide for further research. The work of interpretation is of a technical nature and therefore only experts can do it logically. If the interpretation is not done very carefully, misleading conclusions may be drawn. So any person without adequate knowledge of statistical methods as well as statistical operations and their implications is likely to draw wrong conclusions. In interpretation statistical data, besides technical knowledge, common sense is equally important. A statistician can draw precise inference only if he is fully conversant with the problem under study and its implications. Extra care is to be taken in interpreting results where statistical methods were used. Accuracy in results depends, to a desirable degree, on the personal qualities and abilities of the interpreter. The interpreter must be creative of ideas. He should be free from bias and prejudice. Fundamental principles of interpretation. Following principles should guide a researcher while interpreting his findings. Sound interpretation involves willingness on the part of the interpreter to see what is in the data. Sound interpretation requires that the interpreter knows something more than the mere figures. Good interpretation demands logical thinking. Clear and simple language is necessary for communicating the interpretation. Need for interpretation. Interpretation is the ultimate gist of a research. Why is interpretation needed? The answer is the following. The utility of research findings lies on its proper interpretation. The interpretation of research report is necessary for the following reasons. The research involves the effort to establish continuity in research through thinking the results of a given study with those of other studies having the same abstract principle. It is through interpretation that the interpreter is able to know the abstract principles lying in his conclusions. On the basis of the principles underlying his findings, a researcher can make various predictions about the various other events which are unrelated to his area of findings. Interpretation leads to the establishment of explaining concepts. The researcher's task is to explain the relations he has observed in the course of his study. His work is completed and findings are made. There arises an array of new questions constitute the groundwork for new research undertakings and formulation of new theories which will either modify or replace old ones. It's to open new and wider avenues of intellectual and stimulates the quest for more wider avenues of intellectual adventure. Steps involved in the technique of interpretation. The interpretation is not an easy job. It requires great skill and intelligence. It is an art one learns through practice and experience. The technique of interpretation consists of the following steps. Researcher must give reasonable explanations of the relations he has found. He must interpret lines of relationship in terms of the underlying process. He must be able to see uniformity in diversified research findings so that generalization of findings is possible. If any extraneous information is collected during the study, it must be considered while interpreting the final results of research study. The researcher can consult with those having insight into the study who can point out the omissions and errors in logical arguments. These consultations will help the researcher to do correct interpretation. The researcher must consider all relevant factors affecting the problem at the time of interpretation. Assumptions appearing correct at the beginning may prove to be inaccurate later. So researcher must not be in a hurry while interpreting. Precaution and interpretation, prerequisites of interpretation. Interpreter must satisfy himself that the data used for interpretation are adequate and appropriate. If a sample is selected for study, it must be ensured that the sample represents the population truly. The data used for interpretation must reflect good homogeneity. If there is no homogeneity, comparison between items becomes difficult. Before accepting the data interpretation, it must be seen that there is stability of data. If there is no stability, the same results will not repeat in similar experiments. The data taken for interpretation must be relevant to the problem. It must be ensured that interpretation is done through statistical methods. The interpreter must be cautious about the errors that may arise in the process of interpretation. Errors may arise due to false generalization, due to wrong interpretation. Errors may arise due to false generalization, due to wrong interpretation of statistical measures, etc. So the interpreter must remain vigilant about all such things so that false generalization may not take place. He must use correct statistical measures for drawing inferences. The interpreter must take all those precautions concerning with the reliability of data, computational checks, comparison of results, etc. Errors of interpretation. Errors of interpretation can broadly be classified into two groups. Errors occur when unwarranted conclusions are drawn from the facts available. For example, on the basis of decrease in the import of cosmetics, drawing conclusions that the women have become less fashionable is not correct, and drawing conclusions from an argument running from effect to cause also will result into errors in interpretation. Comparison between two sets of data with unequal base will cause error in interpretation. When conclusions are drawn from data relevant to the problem, the conclusions are to contain errors. Errors are also caused due to false generalization and faulty statistical methods. Errors due to misuse of statistical measures. When conclusions are based on what is true, on an average such conclusions may sometimes lead to errors. For example, attributing the average behavior of a group to every member of that group results into wrong conclusions. When percentages are used for comparisons, it will cause wrong conclusions. If the total numbers are different. For example, suppose the number of students appearing for an examination from two colleges A and B are respectively 1 and 50. If this is from college A, we say 100% result, while even if 45 students pass from the college B we say only 90% result. The conclusions is college A better. This is not a fair conclusion. Thus percentage may reveal wrong conclusions. When index numbers are used without proper care, wrong conclusions may be drawn, since the index number have their own limitations. High value of coefficient of correlation may show high degree of dependency. But sometimes, accidentally, also there can be high value of coefficient of correlation even when there's no relation. The data taken for interpretation must be relevant to the problem. It must be ensured that interpretation is done through statistical methods. The interpreter must be cautious about the errors that may arise in the process of interpretation. Errors may arise due to false generalization, due to wrong interpretation. Errors may arise due to false generalization, due to wrong interpretation of statistical measures, etc. So the interpreter must remain vigilant about all such things so that false generalization may not take place. He must use correct statistical measures for drawing inferences. The interpreter must take all those precautions concerning with the reliability of data, computational checks, comparison of results, etc. Errors of interpretation. The errors of interpretation can broadly be classified into two groups. Errors occur when unwarranted conclusions are drawn from the facts available. On the basis of decrease in the import of cosmetics, drawing conclusions that the women have become less fashionable is not correct, and drawing conclusions from an argument running from effect to cause also will result into errors in interpretation. Comparison between two sets of data with unequal base will cause error in interpretation. When conclusions are drawn from data relevant to the problem, the conclusions are to contain errors. Errors are also caused due to false generalization and faulty statistical methods. Errors due to misuse of statistical measures. When conclusions are based on what is true, on an average such conclusions may sometimes lead to errors. For example, attributing the average behavior of a group to every member of that group results into wrong conclusions. When percentages are used for comparisons, it will cause wrong conclusions. If the total numbers are different. For example, suppose the number of students appearing for an examination from two colleges A and B are respectively 1 in 50. If one passes from college A, we say 100% result, while even if 45 students pass from the college B we say only 90% result. The conclusions is college A is better. This is not a fair conclusion. Thus percentage may reveal wrong conclusions. Index numbers are used without proper care. Wrong conclusions may be drawn, since the index number have their own limitations. High value of coefficient of correlation may show high degree of dependency. But sometimes, accidentally, also there can be high value of coefficient of correlation even when there is no relation between variables. Such correlation is called causal correlation. Conclusions drawn on the basis of coefficient of association may also be sometimes wrong. For example, a positive association between coaching and passing examination may show that passing the examination is due to coaching. The fact that coaching alone is not the requirement for passing the examination is not revealed by the above result. Thus a wrong conclusion is drawn. Review questions and exercises. Unit 20. Research report writing. Introduction. The last step in the research process is writing the research report. Each step of the process is important for a valid study, as negligence at any stage will affect all of the study, not just that part. In a way, this last step is the most crucial, as it is through the report that the findings of the study and their implications are communicated to your supervisor and readers. Most people will not be aware of the amount and quality of work that has gone into your study, while much hard work and care may have been put into every stage of the research. The main difference between research writing and other writing is in the degree of control, rigorousness, and caution required. Research writing is controlled in the sense that you need to be extremely careful about what you write, the words you choose, the way ideas are expressed, and the validity and verifiability of the basis for the conclusions you draw. What most distinguishes research writing from other writings is the high degree of intellectual rigor required. Research writing must be absolutely accurate, clear, free of ambiguity, logical, and concise. Assumptions as to the knowledge of readers about the study must be avoided. Bear in mind that you must be able to defend whatever you write should anyone challenge it. Do not use ornamental and superficial language. Even the best researchers make a number of drafts before writing up their final one, so be prepared to undertake this task. Functions of research report. The purpose of a research report is to communicate to the readers regarding the methodology and the results of the study. It is to convince the reader what has been done and what is the outcome. 1. Research report serves as a means for presenting the problem studied, methods and techniques used, findings, conclusions, and recommendations in an organized manner. 2. It serves as a reference material for future use in the same or related area. 3. It serves as a means for judging the quality of the research project. 4. It is a means for evaluating researchability. 5. It provides systematic knowledge on problems and issue analyzed. Essentials of good report. Following are the principles which should lead to a good research report. Clarity. Clarity is the first essential requirement of a good research report. The researcher should be clear in his writing. Research report writing is a reasoning process. If there is no clarity of thought, there would not be clarity in writing also. Correctness. A research report should be written correctly. Incorrect writing is frequently ambiguous. Some reports may become quite misleading and usually difficult to understand. To write correctly, one has to know grammar. Incorrect writing leaves a poor opinion about the researcher and his work. It also affects the image of the research guide. Brevity. The researcher should take care of the economy of words and concentration of ideas. Repetition and superfluousness will obstruct the lucidity of the report and will interfere with precision and clarity. Objective. The researcher should write an unbiased and objective report fortified by facts. It should not contain sentimental wordings and biased statements. Style. A good research report is one that is written in that style which the audience can follow. The style should suit the focus. It should convince the audience of the truth of the ideas presented. Arrangement. Proper organization of the report is the important ingredient in the whole process. Simply to know that a report has an introduction, body and conclusion is of little use. The real problem is to decide where to begin and what to say next. Consistency. There must be consistency of thought. If there is no consistency in the arguments, then the validity of the report itself will be doubled. Plan. Planning the study materials and processes form the basis of preparing the research report. A well-planned report facilitates proper understanding and correct reading. Preliminaries to report writing. Before embarking on writing of the report, certain preliminaries have to be planned and implemented. The type of readers of the report must be identified. Readers may be from academic community or from general public or some research sponsors. The language, style, and presentation must suit the readers. The purpose of report matters, and must be determined. Report must be designed to serve this purpose. Scope of the report is also to be discussed before preparing the report. Scope depends on the type of readers and the findings. Style of the report and format of the report should also be determined before preparing the report. Significance of report writing. Research report is considered a major component of the research study, for the research task remains incomplete till the report has been presented or written. As a matter, even the most brilliant hypothesis, highly well-designed and conducted research study, and the most striking generalizations and findings are of little value unless they are effectively communicated to others. Following are the aspects leading to the significance of report writing. The purpose of research is not well served unless the findings are made known to others. Research results must invariably enter the general store of knowledge. Most of the universities and other organizations treat the presentation of research results or the writing of report as part and parcel of the research project. Writing of research report is the final step in a research study and as such, requires a set of skills somewhat different from those called for in respect of the earlier stages of research. This is crucial task which should be accomplished by the researcher with utmost care, and he may seek the assistance and guidance